Learners OD2 Reader and Assistance Experience Project. That's L.O.R.A.X for short. To my colleagues Gina, Stephanie, Jafer, Chris, and Adam.
You have to go a little bit closer to the podium. That one doesn't have the great things.
Oh, I see. Apologies.
Just a quick outline of our presentation. We'll be going through the background of our project, the objectives, the requirements from our spec, hardware, software, a video demonstration, and the next generation of our project. A little bit of background of why we are doing this project. Based on this quote.
A little louder, please.
Oh.
Thank you.
Based on this quote, it shows that a lot of new drivers are reckless, and these new drivers have older vehicles that don't have new technology. And in 2018, the backup cameras will be required in all new vehicles, therefore throwing in the support for new technology in vehicles. So we are building a system called the L.O.R.A.X that will increase protection, safety, and help new drivers learn in the vehicle. And we're going to be using the OBD2 port for the L.O.R.A.X to be able to communicate with the vehicle.
Okay, so what is OBD2? For anybody who doesn't know, in your front of the car, typically under the steering wheel, there is a port that looks just like this over here. And it stands for onboard diagnostics. So typically it's used by a mechanic. They'll plug into it, they have error codes that come up on their screen, and that basically tells them what's wrong with your vehicle. So OBD2 is a query system. You can basically ask it for information. You send it a PID, it sends you back what you're looking for. It has 5 different protocols, and it's in every car from 1996 to present. So most vehicles that are on the road now, or probably all vehicles on the road now, would use this protocol. So what is the L.O.R.A.X? We wanted to use the OBD2 port to create a system to help with safety because the information that we can receive from it would be useful for providing updates while you're driving. So it's a system of multiple components. A few of the components would be the forward-facing display. The forward-facing display is located in the front of the car like a GPS would be. And when you look at it, it gives you information about your current speed, which can also serve as a visual cue for you. If it turns red, you're speeding. And it also provides RPM, gas mileage, and the engine temperature. The L.O.R.A.X also provides the user with a rear-facing camera. The rear-facing camera is basically to help eliminate some blind spots, so when you're backing up, you don't hit into things. The L.O.R.A.X also includes proximity sensors. We intended to use these proximity sensors to assist with backing up, where they would let you know if you were too close to an object before you hit it. The L.O.R.A.X provides speed warning. So this is where on the forward-facing display the text will turn red if you're going above what you set for your speed limit. And there's also beeping. This is to get the driver's attention to make sure that they know you're speeding, slow down. The L.O.R.A.X provides a data logging functionality, and this is mostly for the user to look over after to see where their problems are. If they are speeding too often, or if originally we wanted to include tailgating or anything like that, it helps them review what their driving habits are. So some of our main requirements for this project were to have the forward-facing display and be able to display speed, gas mileage, RPM, the rear distance from whatever object is closest to you, and your engine temperature. Another major requirement was to include the speed warning so that we would be able to grab the user's attention and sound an alarm if they're speeding. We wanted to have a rear view camera that would cover basically this distance behind the car, because this is a standard distance that in 2018, when backup cameras are included in cars, this is what they would cover. So we wanted to be able to cover the same field of view. And we also needed to include the data logging functionality to allow the user to review what they've been doing in the car.
So here's a little project overview, high-level diagram of our actual L.O.R.A.X system. Here we have the actual vehicle, and that's going to be plugging into, for power purposes, to our OBD2 module and our power module. And that's going to be powering through UART by 12 volts and 12 volts as well for the power module. And the power module is going to actually reduce the voltage down to 5 volts, which is going to go down to the BeagleBone Black, which is going to power our actual board, which is known as the Onceler. And that's going to power our LCD screen and our proximity sensors. And the black lines, as you see here, some of them have 2 arrows, the others have 1, which means that some of these are bidirectional and the others are just single direction. So, as you can see here, the BeagleBone Black is going to be connected to the Onceler by stacking using the P8 and P9 headers, and then that's going to be stacked the same way for the LCD screen. And the BeagleBone Black is also going to be connected to the camera as well, but using a USB. So the L.O.R.A.X is actually going to be positioned in the front of the dashboard, and camera and sensors are going to be connected to the back, and we're going to be using a trailer connector, which is going to connect to the trailer part of the actual car, and which is going to trigger a signal in order, when it goes into reverse, it shows the rear camera. Okay, so here's a little schematic for the rear assembly. So we're going to have the 2 sensors, and that's going to be connected to the via wire for 12 foot wire to the actual Onceler, and then we're going to have our camera and trailer connector connecting USB and just wire as well. Another 12 feet, as I mentioned before.
So this is the schematic of our design using Eagle. So this is, when we talk about the Onceler, this is the schematic of the Onceler. So the Onceler again is the printed board that we printed on campus and populated, and we have currently working. So on the top left, we have the headers of BeagleBone Black, which is a microprocessor that we decided to use. The center, on the top, we have the audio output. The top right is your level shifting. Bottom right is I2C level shifting using MOSFETs. This is an opto-isolator circuit, and this is our real-time clock. So just really quick as a note, the level shifting basically takes 3.3 volt signal, ups it to 5 volt signal, and then again, when we receive information, 5 volts back down to 3.3 volts so that the microcontroller can handle that. Continuing, this is our physical Onceler board populated. We will briefly go over a couple of images. So this is the BeagleBone Black that we decided to use. So again, this is the top centerpiece right here. This is the audio output circuit. This right here is our surface mount speaker. This is the opto isolator that we went with. Here again, our I2C level shifters. This is our UART level shifter. And this is our real-time clock. And then all the green items here are terminals. So this is the BeagleBone Black, our microcontroller that we went with. These, when we talk about headers, P8, P9 headers, these are what we're talking about. So they're pins, stackable pins that we use. So the red board that you see here is our OBD2 module that we connect to the car to receive information. And this little green board that's hard to see is our linear or switching regulator. So we take 12 volts from the car, and then we're able to power the BeagleBone Black with 5 volts. We can't power the microcontroller with 12 volts, so that's why we do that. So here's a photo.
While we're talking about this, I'll come around with the actual device and you guys can look at it.
I'm gonna ask that you not touch it, just because we have some static protection on it that would like not to break it.
So here's a photo, obviously side view of the board. So when we talk about stack, we literally mean stacking the board. So on the bottom here, it's a BeagleBone Black, the microcontroller, ADAS in here. The center board is the Onceler, and the top is our LCD screen. We have buttons here on the screen. The red board on the right, again, is our OBD2 module, and then the power module. So we put everything on a consolidated board just for our ease of use and manipulation. Lastly, here's a top view of our screen. The screen is 4.7 inches diagonally. It is not touchscreen, but we do have buttons here for the user to control. So again, this screen is off of our device, so there's no data being shown.
As you can see, this is where we connect to the vehicle itself, and this is our power line here, as well as our case.
I'm gonna wait a little bit for Cal to come all the way around.
You guys have any questions at this time while I'm still walking around? Yes?
I noticed that you had 5 volts going to the BeagleBone Black and then 5 volts and 3.3 volts coming off of it.
So this is yes.
The car's only 3.3 volts.
Yes, it does. But the 5 volts is straight to the power module.
Now I'm going to cover the high-level software requirements that we have for this system. So the first thing that we needed to be able to do, and the software needed to be able to do, was request OBD2 codes to the vehicle and read them back from the OBD2 UART module. We also need to read, or first we need to request to the I2C sensors, the proximity sensors, and also read proximity sensor data back. We need to be able to also read the raw data in its raw form and convert it to a form where we can be able to use it. So, for example, the RPM OBD2 data comes in at quarter RPM, so we need to divide that number by 4 to get actual RPMs. After that, we need to be able to display that data to the graphical user interface, to the display to the screen. And we also need to be able to log the specified data that's part of our requirements. One example of logging data is whenever the speed warning is set and the driver has exceeded the speed, then it's then logged into a text format onto an SD card that's part of the that's plugged into the BeagleBone. After that, we also need to be able to generate audio once we've detected a warning has taken place, such as a speed warning. We also need to be able to detect when the vehicle is in reverse with software, and also, once that happens, we need to be able to display the camera to the screen. Yes, Dr. Joe?
Tell me more about the specified speed limit. Is that hard-coded in? Is it adjusted automatically? I mean, we talking if you go over 70 miles an hour and you don't get an alarm even if you're in a school zone? How flexible is the specified speed limit?
Okay, so the idea behind the speed limit is for maybe companies who have company vehicles and they don't want their drivers to be going over a certain speed limit. And so, or parents, if your parents don't want your kids to go over certain speed limits on the road, like, you know, they're going 90 and something's wrong, right?
So this is a codable absolute maximum, not context sensitive.
That is correct. Did you want any more information on that, or?
No, I'm just being mean.
Okay. Thank you for your question. So, as I was ending up, we need to be able to display the rear view from the camera to the screen. The development environment that we used for this project is on the BeagleBone Black. It comes with the Linux version, 7.8. What we did was we actually upgraded the Linux version to 7.9, so we have Debian Linux, right? Sorry, Debian Linux. We used C++ 11 for our programming languages. For all of the programs, except for some of the initialization files and the audio file, which we use bash scripts in order to do that, and that pairs with Linux. The C++ libraries that we use are OpenCV 3.0. That was used for the GUI display and also for the camera display. The thread library we used instead of pthread. It is a new library to C++ 11, and it made our lives a lot easier. And we also use glib for the GPIO interrupts for the reverse detection. Our version control that we used was GitHub. We used that to save our code and update it and be able to see changes. When we first looked at the problem of how we're going to design our system, we needed to be able to do basically 3 things at once. We broke our system into 3 compartments of things we needed to accomplish with the software. So the first thing that we needed to accomplish was we need to get the information. And so the query thread that we have gets the information from the OBD2, it gets the information from the real-time clock, and it gets the information from the proximity sensors. That's raw data. The other compartment that we need in the software is the data management. That data management is in charge of receiving the raw data and converting it to a logical format. It's also in charge of unit conversions. For example, if you want miles instead of kilometers, because the OBD2 UART comes in the standard units of SI units, sorry. The SI units for kilometers and things like that. So if the user is obviously in the United States, they want to see miles per hour. That's where that's handled. The data management thread also handles the detection for the data logging. So once the speed limit is exceeded, that is where the data management, that's where the data logging happens. And it's logged into an SD card as a text format through Linux syscall. Then the graphical user interface thread, we need to be able to display the information to the user as well as display the camera, and that's where that's handled. Yes, Dr. Jeff?
I'm curious why threads rather than asynchronous communicating sequential processes?
Can you repeat the question?
Well, 2 major software approaches to achieving concurrency. Independent processes or threads within a process. I'm curious as to why you chose threads rather than processes.
I can answer that question. The large reason why we decided to go with threads rather than processes is because of the ability to use shared memory. We are using quite a few globals. Okay.
Good. Excellent.
Of course.
This is a very simple high-level diagram to support the data flow that's happening. The vehicle parameters are coming from the vehicle or the sensors, and they are queried from the query thread. The query thread then stores the information as the OBD2 codes as the raw data. The data management thread then reads the raw data and the OBD2 codes and then converts it to logical formats into the converted data, where the GUI can then read from those converted data and be able to display it. And Jacob now is going to wrap up how we tested the system and how it's working currently.
Okay, thank you, Chris. So as you can see, we have our actual L.O.R.A.X device here. Our OBD2 port, which is going to be connected to our card, is connected to our module. Then we have a cigarette lighter, which is connected to our, it's hard to see here, but it's connected to our power module, which is then actually attached to this jack, which is then going to be connected to the vehicle light. And then we also see here a white wire, which is a USB, which is connecting the camera to the vehicle in black as well. And then we also have a USB micro. This is for testing purposes for to connect to a laptop. So here we actually have the trailer connection. This is used in order to send a signal in order to trigger the reverse. When it goes on to reverse, it will have the camera just show up on the screen. And then this is also the OBD2 port that I was talking about, which is located underneath the steering wheel, and then the cigarette lighter.
Okay, now we'll do a demonstration, and it'll be in video format since we need to be in the vehicle to actually run our system. So should already be open. So when the system starts up, we display the initialization screen, and this is so that we can acquire initial data from the vehicle before displaying any data. And once the initialization phase is completed, 4 values will be displayed to the screen. For this demo, we're displaying speed in kilometers per hour, revolutions per minute, engine temperature, and in degrees Celsius, and also the time. So once the vehicle is in reverse, you'll see that the reverse camera is displayed to the screen. And the camera view does not fill the full screen, and that's so that we can preserve the aspect ratio and we don't get a stretched image. Once the vehicle is put back into drive, the system will once again display vehicle data. And as you can see, the update rate for our different values is actually pretty slow. It's about once per second. And this is largely because of the rate at which we can query values from the car itself. And unfortunately, this actually is a huge limit on what we could do with our system, on the rate at which we could change these values.
What's a huge limit?
You pause the video. One of the big things was that, for example, we wanted to be able to determine if you were accelerating at a rate that was unsafe, and since we couldn't query our vehicle quickly enough to determine if you were accelerating too quickly, that was one of the things that was limited by this issue. Yes.
So is it a limitation of the OBD protocol? Or?
Yes. So we actually looked into a couple of options to remedy this. Namely, there's a monitor mode for the OBD2 where you can actually just monitor the CAN bus. And we tried to do that, and it didn't work out very well. We weren't actually able to get any data. And unfortunately, the documentation on how OBD2 works in different cars is very limited because it is dependent on company and vehicle. So generally, companies aren't very willing to release data on how they work. So that was one of the big problems that we had.
And can you also not get the gear of the vehicle from
Yes.
OBD?
Yes, that is not a standard thing that you can get from the vehicle. There may be some vehicles that allow you to receive that, but like I said, the documentation is not very good, and so it's hard to tell which vehicles would allow that. Okay, Jeffrey. So for this demo, the user specified speed limit is set to 65 kilometers per hour, which is approximately 40 miles per hour. And when the speed limit is exceeded, the audio warning will sound, and the color will change to red. And this color will stay red until the speed limit is no longer being exceeded. At this time, also, the data will be saved to the data log, indicating what time the speed limit was exceeded, and then again, what time the speed limit was no longer being exceeded. Please skip to 4. So the other values that our system can display that aren't displayed here are the gas mileage and fuel level. And once again, the vehicle is placed into reverse, and as you can see, this greatly improves the driver's visibility out the back of the vehicle and helps with parking in reverse, for example.
Is that a reversed image like you would see in the mirror, or is it a true image from the camera?
That is a, if you look at the screen, it's the right-hand side of that screen is actually going to be your left-hand side. So if you're looking at it like this, it would be as if you were looking in a mirror. Okay. That's a demonstration. So data logging. If you noticed during the demonstration, we exceeded the speed limit, and we actually did this demonstration, filmed it today. So as you can see, we've logged data from today, Friday the 29th, at around 10:25. We exceeded the speed limit, and then we again were underneath the speed limit. And this data is logged into just a simple text file, which is stored on the removable SD card of the vehicle going black, and is available for somebody, the user, for example, a parent, to go back and look, has my child been speeding, things of that nature. As of right now, there's no way for us to automatically clear our logs, so it will continue to fill unless you delete the file or somehow clean it. And also, another shortcoming of our file is that there is no protection on it to prevent someone like a child from taking that data and erasing it to cover their tracks. So now we'll talk about the next generation of this project and some of the things that we were unable to accomplish during our project, as well as some of the things that we would have liked to implement in a a future project that went along these lines. So the first thing is our I2C sensors. We were not able to get our sensors to actually give us meaningful data over a long cable, and we believe that this issue came forth purely because of the sensors that we chose. It took us a little while too long to figure out that our sensors were not good, and so we were not able to, with the time remaining, change our sensors to better ones that we would be able to utilize. Also, as I mentioned previously in answer to Dr. Lyle's question, the rate at which the OBD2 can be queried hinders our ability to log data such as dangerous acceleration and deceleration. So in the future, we would perhaps add an accelerometer to our project so that we could detect if you were in fact accelerating at a dangerous rate. And lastly, before this product could actually be sold, we would need to add the ability for the user to actually manipulate what's being displayed to the screen, as well as choosing their specified speed limit. And that would have been done through the GUI. So in conclusion, we've created a successful project, a working L.O.R.A.X system, and it has a great foundation for future work. We also felt that our system could bring actual safety to older vehicles that do not have systems such as the reverse camera or something to determine when you are in fact speeding, as well as at a price of, at an estimated price of $381 for this system. We believe that it's a great option for people who are looking at buying a older vehicle that does not have these features rather than purchasing a brand new vehicle, since it does allow things such as acquiring data from the vehicle, the audio for when you're speeding, and also the data logging, which could, the data logging is actually one of the parts of this project that could be utilized in many different ways. For example, we could in fact log more data such as what our RPMs were for the entirety of a trip or something along those lines, as well as the rear view camera and the graphical interface make our project something that people may want to purchase. Are there any questions? Yes?
Is there any provision in this system for displaying the fault codes that come up when your check engine light comes on to alert the driver when the fault is?
As of right now,
Easy to do.
As of right now, we do not have that capability, and we haven't looked into it. But I believe that there are PIDs that you can use to ask the vehicle, why is my engine check light on? There are actually certain apps, I believe, that you can do that with. So our system could probably implement that fairly easily.
Also, one other thing I wanted to add is in terms of future generations of this project, I think it's an ideal opportunity to bring in a mechanical engineer and make a multidisciplinary project because you've got serious packaging issues
Yes.
going on with your project. And if you want to put it in a car, you want to have a nice looking, well-mounted, solid, vibration resistant. You can actually do some environmental tests on it. So
Yes.
I think that probably I might want to add that to your list of things to do on the next area of projects. Is try to recruit a mechanical engineer for the project.
I would agree. Any other questions? Yes, Dr. Brew.
So that's very interesting, by the way. Listen to what you are saying, and then look at the evolution of this and how it kind of commercialized. It seems that the dominant restriction is all the wiring that's going on.
Yeah.
And the second part is you really need a vehicle block. I didn't see the need for that kind of computation horsepower based on all the things I saw you were doing.
Right, so when we first chose our BeagleBone, we didn't realize the limitations that the OBD2 would put on our vehicle, and we thought that we would be querying data much more often. And so that's one of the big reasons why we went for microprocessors that had a little bit more processing power, which was so that we could handle having 3 different threads running at the same time, one of them displaying a camera, as well as querying data all at once at a fairly fast rate. So that's kind of why we went with that. And the other question about the cables, it was actually several of us brought up more wireless solution in our prelim, and we actually just went with this design mostly because it would be more achievable for a team this size in a semester. But it was something that we considered was a more wireless approach to this.
I'd like to show my mean streak and follow up that question. Were you not familiarizing yourself with the OBD protocols during prelim to the point where you would know before you went into detail what the rates of that protocol were?
Right, so we did actually look into what PIDs we could get from the vehicle so we could kind of get an idea of what information we could get. But as I said before, the documentation on OBD2 is very manufacturer specific, and so we were not able to find any information on how quickly you can query at all. And so it came down to trying it out and finding out that there's a certain speed at which we could not query and get
So
data.
there's no published specs on that?
There,
Standards for that system?
there is a standard for the system, but it's not used by the manufacturers. It's largely ignored, in fact. I think I saw a question in the back there. Did you?
Oh,
Yeah.
yeah. So I believe you talked about it earlier, though, with your query problem,
Mhm.
where you weren't able to update your information as quickly. What was the main reason for that again? Why couldn't you update your information
Right,
as
so-
fast as you wanted to?
So the way it works is that we have our module. We can go back to it real quick. So this module is what allows us to talk with the vehicle, and we actually communicate this module via UART, and then this module communicates with the vehicle using the OBD2 protocol. And the problem that we ran into is that when we ask for a value, when we ask for a data, it will give us back that data, but if we ask again too quickly, it will actually not give us meaningful data again. So the big problem was not actually asking for the same data twice. It's if we want to query for something such as the speed and then the RPMs. If we query the speed and then too quickly query the RPMs, it'll actually give us back speed again. So it'll give us the data back on speed. Yes, Dr. Jaffe.
I don't have any specific concerns in mind, but I'm wondering if you did any sort of hazard analysis. You're putting gear on a potentially lethal device. Are you satisfied that there is no possibility? Why are you satisfied that there is no possibility that any malfunction of your hardware or software could not cause anomalous behavior in the overall vehicle. Did you do such an analysis?
We did not do an analysis of that form. However, when we were researching the LD2 protocol, it does state that while you can query for information, you cannot write to the vehicle. So, for example, our system could not control the acceleration of the vehicle according to the OBD2 standard.
So the answer, I think, is, and it's a good answer, that your digital interface to the vehicle, if the protocol that you are adhering to is correct,
Yes.
cannot result in false signal injection or hazards, indirect hazards. Okay, I'll buy that. I'm sure you understood every word I just said.
Of course.
In the future, I would document hazard analysis for such things.
Okay.
Any more questions? So is this board is just specific to reading the OBD stuff from the car?
Yes.
Is there level shifting going on in that board? Rates established by that board? What all is the board doing?
We can actually, we can set the baud rate of the UART to this board. However, all of the CAN bus protocol is run by this board and we don't have control over that. That's what you're asking. Yeah, so.
That's what actually talks to the car.
Right, so we actually have to, we communicate with this board using UART, and if we want to configure the board itself, we use AT commands. And for those who aren't aware, AT commands are just a protocol that is used by certain devices where if you want to communicate with the device itself, you specifically send the letters AT followed by a command. That's the name AT commands. If we want to communicate with the vehicle itself, we will just send the OBD2 PIDs.
Looks like we have lots of time right
Yeah,
now.
yeah, plenty of time.
So, let's hear a little bit from some of the other folks in the group. So maybe I'll throw a question to each of you to say something first. Knowing now what you do know, in retrospect, if you were to go back to the beginning, what one thing that you learned would you do differently?
I'm still thinking.
Unless you did it all perfectly.
Well, no, of course not.
I have one. While other people kind of think of their answer, it definitely has to be the I2C sensors that we used. Actually, we don't have a very good picture of them in here, but they kind of look like this. SRF-08 I2C sensors, they were very problematic for us, and it was namely getting communication back from the I2C sensors was a large problem for us. So I think if we could go back and start over again, we would have selected different sensors. Potentially, yeah. We probably would have gone with analog sensors rather than I2C.
I think board layout could have been a little better. I think we could have done a little bit better research on how standard flows are laid out. We had that's a 4th gen board. So if you see the blue wires, we actually had to cut some traces and use those to reroute. There are a couple surface mount items on, capacitors that are not surface mount by through holes. We would have liked to use surface mount, but we didn't have any of the value. We didn't have most of the values that we needed, so we just went ahead with through hole with that. We do have a board layout that's in a .brd file that's all surface mounted, but we don't have that print. And then I think we could have implemented some wireless communication. Maybe not a lot, but at least attempted some of it. So yeah, that's what I would like to see.
I think just being limited by number one budget and the amount of time we have this semester, that's kind of how this project came about the way it did. But without a lot of limitations and things, I think we would have done a lot of things very different. And one of the big things would be wireless communication, because anybody that would actually buy this for a safety system for their car is not going to want to run the camera from the back all the way up through to the front. So this is more just because of budget, semester, everything like that. But there's a lot of things we could have done different on this project.
I would agree with Gina that having a wireless interface would have been more user friendly.
In my opinion, I think for our power system, we could like implement it into our actual board instead of just having a module on the side doing all the power configuration.
I actually have something to add on to that. The way that we have it configured in our current system is that we pull power from the vehicle through the cigarette lighter. At one point during our project, we actually ended up using the power that comes from the OBD2 itself and through our breadboard here. And something happened to our first module, and we're not quite sure what happened, but we somehow broke it, and so we were a little bit nervous to try that again. But we did have it actually powered just through the OBD2 at one point. So I think we would revisit that and see if that was still a viable option. But with the time we had left, with ordering a new one of these red modules, we didn't revert to that method of powering our board.
I would have handled the data differently from a software perspective. What we're doing now is we're storing the data in globals and we're reading them from globals. If I would have gone back, I would have spent a lot more time making sure there's a more concise solution to handling the data, such as message passing between the threads and other things like that.
Well, let me make a comment for you. A bunch of you were leaning toward a wireless solution to this thing, and I'm kind of an RF guy, and that notion scares me a little bit because presumably you're going to sell this thing to everybody. There's going to be one in every car, probably one in the car that's next to you at the stoplight. And balancing the communications to make sure you're talking to the sensors in your car and not talking to the sensors in the other car now becomes a whole brand new can of worms. And quite honestly, I've seen installations of stereos in cars that are more complex than what you're talking about here. If you've got a good installation kit and good installation instructions, anybody in the stereo shop could probably do the installation for you. So I think that the jump to wireless is a very risky jump. It should really be thought through very carefully. Risk-reward analysis, as opposed to taking the time to say we have an installation procedure, an installation kit, and here are the connectors, and here are the instructions, and maybe talk to somebody in a stereo shop and say, could you do this? If we gave you these instructions, could you install this in the car? Chances are they'd say, yes, snap. So be careful about jumping on that wireless train too quickly.
Jeffy?
If you're going to do it wireless, get some of the cyber intel security types.
I think they got that, Matt.
Yeah, so I'm curious as to what sort of software testing you did. For instance, you mentioned that you were using multiple threads because you wanted to use the shared memory aspect of it. So how do you know you didn't have any synchronization errors or stuff like that? Did you conduct unit tests?
So, the way that we have our globals designed is we're never writing to the same variable across the threads. And so we felt that was adequate enough for us, and this not being a hazard to the vehicle, and that it's not going to impact the safety of the driver, that we didn't have to further test whether or not there would be write errors or read errors between writing at the same time, because we're not ever writing to a variable at the same time.
Yeah, I guess I was wondering, did you have any test drivers you
Oh, right. I did have a test driver that basically inputted values and simulated the OBD2, but we weren't actually able to fully simulate with the OBD2 because we can only get it from the car. And the OBD2 emulators are very, very expensive. They're more expensive than our entire project. And so I was limited on that. So I was able to create test drivers for just simulating the data, but not actual testing the drivers because we need to be able to be in the car.
Any more questions?
okay.
Any more questions from the audience?
Yes.
You guys had some sort of budget limitation for this project?
Right, so obviously as a capstone project, our money is not limitless. I think we were supposed to try to keep it under $800.
What should we spend?
Around 500 or 600. Yes.
Oh, so correct me if I'm wrong, but I was noticing during your guys' demonstration video that initially when you went over that upper bounds for speed, it started to beep, but then after being past that upper bounds for a little bit, it stopped beeping. Was I correct in my observation?
Right, so that was actually by design. It beeps 3 short beeps 3 times when you cross the threshold, and then it doesn't beep again.
So then my question is, do you see that as some type of safety hazard, and do you see a way to remedy that?
Are you saying that we should, in fact, have it beep continuously while you're over the speed limit?
Well, if I'm a driver, I mean, I want to be notified. I'm not going to constantly looking at something that's not the road.
So the tone that you heard is not actually, it's actually limited because it's in a box first off, and then the camera is sitting.
Okay.
You're just looking through little peepholes, look at the physical LCD. The tone is actually very obnoxious.
Okay.
So we learned that really quick in the lab. So we thought that that was pretty significant enough to alert the driver.
Okay.
And in a case when a user is driving and maybe they incorrectly set the speed limit, but they have to exceed it because they want to safely drive above the speed limit, we don't want the device to become a distraction and further distract the driver in a case of user error.
By the way, you just did some hazard analysis.
Any more questions from the audience? Okay, then, like Professor Brewer asked you, I'd like to get each one of you to answer this question. It's not so much about your project, but what we have in the audience is a lot of people who are going to be doing capstone in the future. Okay, so if each of you could have one piece of advice that you would give to somebody who's going to do capstone 12 months from now, what would that piece of advice be?
No,
Don't procrastinate. just don't do it. Don't wait till the last moment to start writing up your actual proposal or stuff like that. Yeah, learn that the hard way.
Communication is very important in a team. Always keep up communication.
Yeah, definitely don't procrastinate, and you will spend a lot of time in the design lab talking to each other. So maybe get to know each other a little bit first and like who you're working with, because you will be a lot.
I would say communication is a big factor, huge factor on efficiency. I mean, massive. If you can really communicate well with your team, then if one person is working on a portion of the project, and then later on in the day somebody else is working on it, then you don't have 2 coinciding thoughts that are disagreeing. And then on top of that, keeping up your own part. So doing your own research. So if you're a double E, then you would want to research if you've never used Eagle before. You know, get a head start on that. Don't wait until, oh, we have to start this today. Let me do some research right now. Do it the night before or a week before.
Could you elaborate a little bit on what kinds of communication should be employed to make things run smoothly?
So I would
Verbal,
say
written, text, message,
yes.
Phone messages, what?
I would say written communication on, so we have the whiteboard and the SDL, you know, write things that you think that people will forget. So if you mentioned, hey, can you edit this document? Have a priority list of things that need to get done for the week and then for that day. So we have priority lists for SEs, and double E's because we're full NCs, SEs and CEs and double E's because we work on separate tasks. But then again, we also work on documentation together as a whole. So there are a couple things that everybody works on here and there, and then a couple things that 2 people will be working on. So I guess a priority list and really communicating with the whole team on what really needs to come out of this. Because you don't want to be sitting there arguing with one other person, well, I think this needs to happen. No, I think this is what needs to happen. Okay, well, the team lead isn't here, or the rest of the team isn't here because it's 10 o'clock at night. So then you have to wait till the next day, and then things don't get done. Hopefully that answered your question.
I would say during the prelim stage for the proposal, you research a lot into your proposal. During the design phase, the detail phase, going into detail, I think one of my shortcomings was like I stopped researching as much as I should. I didn't continue researching what I needed to work on, and I just kind of went with our design how it is instead of further trying to refine it into something better.
As far as advice goes, I would actually talk about some of the things that we did well. Number one, I would say is that when you're working on your project, do it together. So even like one of the big things that we did well this semester was that when people had homework or anything like that, they were in the design lab, we were all in there. Even if we weren't working on the project, the fact that we were together made it easy for if somebody was working on the project and someone else was doing homework, could just walk over, like turn around and say, hey, can you do this later? Or hey, can you help me with this really quick? Being in the same proximity as everyone when you're working was one of the big things that worked out really well for us this semester. And I felt like if we had not been, if we'd done something along the lines of, oh, I'm going to go home and work on this, or I'm going to go work in the library on this, or somewhere I'm going to work with my friends that aren't in this project with us, it would have been much more difficult for us to accomplish what we did this semester without that. Also, one other thing, try to remember that you do have paperwork to do in detail. If you forget about that, it makes your last couple weeks more difficult.
Are there any more questions from the audience?